Okay, I want to have a look at this question here from your class test. It says candle wax burns in oxygen to form carbon dioxide and water according to the following balanced equation. So this is the exciting formula for candle wax. Plus 35 oxygen goes to 23 carbon dioxide and 24 water. We know if we ever burn anything in oxygen, we call it combustion. So this is the combustion of candle wax. In one such reaction, 4,86 times 10 to the 22 molecules of candle wax reacts with 3 moles of oxygen. Define the term limiting reagent. So limiting reagent, it's not in the exam guidelines, but I would accept anything like the chemical reagent that is used up first in a chemical reaction, or the chemical reagent that controls how much product is made, or anything that appears like that, because it's basically exactly what a limiting reagent is. Then it says to you, determine which of candle wax or oxygen is the limiting reagent. So obviously to do this, we have to, as we always do, find the moles. But how are we going to find the moles? So this says molecules, and we know that in chemistry we have a handy formula that says molecules to moles, because we didn't want to use these large numbers of molecules, so we use Avogadro's number. So the number of moles is equal to the number of molecules over Avogadro's number, which we will find on our data sheet. So here we've got 4,816 times 10 to the 22 molecules of candle wax over Avogadro's number. Okay, and that will turn molecules into moles. This is the original formula that you learn when you learn about moles. So this gives you 0,08 moles of candle wax. Okay, so now if we want to find out what is the limiting reagent, we have to have a look at the mole ratio. So it says to you here, if we look at the mole ratio, we have 1 candle wax, and I'm just going to write candle wax and not the whole formula. We have 1 candle wax to 35 oxygen. So if we put all of this candle wax to the flame, we would have 0,08 candle wax, and it is in a ratio of 0,08 times 35, because there's 35 times more oxygen moles being used, and this is going to give you 2,8 moles of oxygen. So if we have a look here, it says to you there are 3 moles of oxygen. So the candle wax only needs 2,8 moles of oxygen. Okay, but we have 3. So if we have 3 oxygen and the candle wax only needs 0,2, okay, that means the candle wax is limiting because it's in the smallest amount. So now the candle wax is now controlling everything in this chemical reaction because it is my limiting reagent. Okay, so let's have a look what happens next, because this is pretty straightforward. You just found the moles, you looked at the mole ratio, you figured out we've got more oxygen than we need, so oxygen is in excess, and if oxygen is in excess, candle wax is limiting. Okay, now it says to you that the percentage yield of carbon dioxide is 90%. Okay, so we know that if we look at percentage yield, it will be my actual yield, what we actually get in real life, over my theoretical, okay, multiplied by 100, because that's how we turn it into a percentage. So you need to ask yourself, where do we get the theoretical yield from? And the theoretical yield is the maximum possible from the balanced chemical equation. So if we were to have a look here, let me do the second half of this in a different color. If we were to have a look here, we would say now, what is the theoretical yield of carbon dioxide? So the theoretical yield of carbon dioxide, okay, comes from the balanced equation. So what is controlling this equation? The candle wax is controlling this equation. So 1 mole of candle wax, which we're going to call C-wax for short, reacts with oxygen to produce 23 moles of carbon dioxide. So how many moles of candle wax did we have? We had 0.08 moles. So this is going to be 0.08 times 23. This is how much carbon dioxide we can theoretically produce. So this comes out to 1.84 moles. Okay, that's how much is our theoretical yield. So it says to you the percentage yield of carbon dioxide is 90%, and they want you to calculate the actual volume of carbon dioxide collected. So if they want you to find the volume of a gas, you know that you have to use N equals V over Vm, because this is the only formula we've got linking volume of a gas to moles. But it says to you the molar volume of the gas is 23.2, because we know at STP the molar gas volume is 22.4. It's on the data sheet, but here we have 23.2 because we are not at STP, we are at 27 degrees. So in this formula, if we use it, we know our theoretical yield is 1.84 moles. Okay, so it's going to be 1.84 equals the volume we will produce over the volume 1 mole occupies. So we're going to produce more than 23 cubic decimeters of gas because it's more than a mole. So if we put this into the calculator, we get 42.688, and this will be in cubic decimeters. So we've produced 42.688 cubic decimeters in a perfect world. This is our theoretical carbon dioxide yield. So what is our actual yield? Our actual yield, they said to you, the yield is 90%. So we just have 90% of 42.688. That is what we are going to produce. Okay, and that will give you 38.4192, and because this is our final answer, we can round it off to 38.42 cubic decimeters of carbon dioxide. If you wanted to, you could go back to your original formula here, and you put in here 90 equals actual, which we're trying to find, you can call it X, over the theoretical, which is 42.688, okay, times by 100, or you can just say what is 92% of 42.688, and you will come up with your final answer here, which is 38.42 cubic decimeters of carbon dioxide. And it's wonderful because you never once had to calculate the relative molecular mass of this interesting compound, which would have been a very large number.